What if the Big Bang wasn't the beginning at all, but rather the echo of something much larger? In 2025, the James Webb Space Telescope's JWST survey analyzed 263 early galaxies and found that about 60% showed the same apparent spin direction, 158 clockwise compared to 105 counterclockwise. This is not what a random universe would be expected to produce. It's an observation with two possible paths. Perhaps the imbalance reflects measurement bias, or perhaps it points to a radical new cosmological picture. If true, it would force a serious rethink. If not, it still shows us the limits of what we can measure. And this is where an unusual alignment in the sky begins to raise deeper questions. A strange alignment in the sky. In early 2025, a research team examined one of the deepest James Webb Space Telescope fields, known as JWST, and their results quickly drew attention. Among the 263 spiral galaxies observed from this region, objects that formed only a few 100 million years after the Big Bang, 158 appeared to rotate clockwise, compared to 105 rotating the other way. That works out to nearly 60% sharing the same orientation. Statistically, the imbalance carries weight. The asymmetry corresponds to a one-tailed binomial probability of about 0.0007, or roughly 3.4 sigma. That means the chances of seeing such a strong tilt purely by accident are less than 1 in 1,000. Cosmologists normally expect roughly equal numbers of clockwise and counterclockwise spins on large scales. Webb's field shows a clear departure from that. The published analysis used an automated, symmetry-tested algorithm to classify each galaxy's handedness, and the team mirrored the galaxy images as a check. The preference for clockwise rotation remained regardless of method, reinforcing that this was not just a quirk introduced by the measurement process. This imbalance stands out because cosmology has long assumed that when matter collapses under gravity to form galaxies, no preferred direction should survive. The guiding principle is isotropy. On a large enough scale, properties of the universe should look the same everywhere, without favoring a particular orientation. Equal distribution of galactic rotation directions seemed like a natural outcome of that assumption. Yet Webb's observations point to an organized tilt already visible in some of the earliest galaxies, suggesting that these structures did not emerge as independently as once thought. The scale and distance of the galaxies only strengthen the puzzle. These are not nearby systems where interaction with neighbors could explain alignment. They stretch across vast spans of the early universe, separated by billions of light years, with no direct way to influence one another. For such distant galaxies to share the same spin tendency implies a cause operating at scales far exceeding known gravitational interactions. It is not easily dismissed as a local effect. It appears baked into the fabric of cosmic structure itself. The implications extend directly into the foundations of cosmology. The lambdictum model, the standard framework explaining how structure grew from random density fluctuations, does not predict any preferred spin direction. Within that model, the universe begins essentially isotropic and irregularities evolve statistically without global bias. Seeing a consistent departure from randomness introduces tension with the picture that has guided theory for decades. A phenomenon resilient across multiple galaxies, billions of years in the past, hints at either missing physics or influence from conditions present before the first clusters emerged. For some, the Webb results signal more than a minor adjustment. A preference on this scale could indicate that the universe carries a memory established at or even before its visible beginning. If rotation directions across an otherwise random cosmos show a coherent lean, it challenges one of the most basic assumptions. That orientation at large scales should cancel out. The fact that it does not injects a sense of order where none was expected. At the same time, the community remains cautious. Researchers know that interpreting faint, ancient light carries risks. Light from galaxies at extreme redshift is stretched and distorted as it travels across expanding space. Identifying rotation from such images requires both subtle measures of structure and corrections for noise. That is why the JWST team built in checks such as automated classification and mirrored images, ensuring results did not arise from human interpretation. Despite that, not everyone accepts the outcome as definitive. Large findings demand replication, and many are waiting to see whether other surveys confirm the same trend under independent conditions. Yet the fact remains, this is no small fluctuation. Across hundreds of galaxies, the skew appears persistent, and statistical treatment places it well beyond what simple chance should allow. In physics, when a result resists explanation within known frameworks, it often becomes the trailhead for new ideas. Whether this asymmetry proves to be a measurement issue, an incomplete theory of galaxy formation, or evidence of something fundamental about the cosmos, it has forced astronomers to contend with possibilities they rarely expected to face. The lesson history has given science is that small irregularities can grow into breakthroughs. Subtle departures in Mercury's orbit once helped spark Einstein's general relativity. Unexpected results in particle experiments reshaped physics through quantum mechanics. Now, a quiet imbalance in spin orientation may play a similar role in cosmology. Whether it points toward hidden physics, novel early universe conditions, or a larger geometry that orders galactic motion, it demands attention. For observers, it is striking to consider that galaxies across immense stretches of time and space might share a single preference. If the pattern continues to hold, the symmetry of the universe itself, long regarded as unbroken, may be less absolute than once believed. This does not mean the standard model collapses at once, but it introduces strain at a critical point, the very origin of visible structure. If isotropy fails even modestly this early, the underlying principles of how galaxies first spun into being may rest on deeper causes we cannot yet see. The discovery leaves astronomy at a crossroads. On the one hand, a tangible dataset is challenging conventional expectation. On the other, scientists know every new instrument can reveal artifacts until methods mature and confirmations pile up. The proper stance is caution, but also curiosity. An anomaly this sharp cannot be ignored. It forces scientists to ask whether the skew is real, and if so, what hidden mechanism wrote directionality into the design of the cosmos. And so, while the Webb data opened the door to striking ideas about symmetry and orientation, the harder task lies in deciding how much of this signal belongs to the universe, and how much may belong to the difficulties of seeing it. Error or illusion? When scientists confront results that challenge expectations, they first weigh two competing explanations. A, the imbalance is a product of measurement or selection bias, such as Doppler brightening, image faintness, or annotation errors. And B, the imbalance is real, caused by some underlying cosmological mechanism, possibly even inherited rotation from a parent black hole. These two possibilities frame the current debate and set the ground for how the evidence is being tested. Among the most immediate suspects is the way light reaches us across cosmic distances. A spinning galaxy has one side moving slightly toward Earth and one side moving away. The side edging closer appears a little brighter, while the receding side dims slightly. This Doppler-related shift makes one half of a galaxy stand out, which can make classification of spin direction easier in one orientation compared to the reverse. Studies long before Webb flagged this type of photometric bias as capable of inflating apparent asymmetries. If at play here, it would not point to a new cosmic law, but to the subtle tricks of light on its way to our telescopes. Alongside that sits the challenge of working with objects at the very limits of visibility. The galaxies observed in the JWST sample are faint, stretched thin by cosmic redshift, and in many cases resemble smudged arcs of light rather than clear spirals. When one arm fades into noise or the image appears lopsided, computer algorithms, and even human inspectors may misread the sense of rotation. A handful of such uncertainties might not matter, but applied to hundreds of galaxies, missing data could accumulate into what looks like a pattern. Astronomers have seen this before. Heavy reliance on faint imagery can plant artifacts that vanish once deeper exposures appear. Another concern arises from how classifications are made. Human judgment has always been part of astronomy, and even machine learning systems often reflect the biases of their training sets. If ambiguous shapes lean toward one designation slightly more often than the other, those small deviations spread across many objects to generate a broad imbalance. That is why, when the Webb findings were released, many specialists paused. They noted that an innocent classification bias or systematic skew in the algorithm might be able to produce the very tilt that seemed to call the universe into question. There is also the historical caution of anomalies that withered as instruments improved. Radio bursts once declared as extraterrestrial signals came from malfunctioning cables. Early pulsar data that confused astronomers turned out to be artifacts of interference. Each decade of astrophysics has witnessed discoveries that later dissolved into technical corrections. This history reminds researchers not to leap from irregularities straight to cosmic revolution. What seems meaningful may, under another lens, look like error disguised as order. Yet the Webb imbalance has not gone away under scrutiny. Teams reprocessed the images using alternative algorithms, applied mirrored controls to counteract potential selection effects, and double-checked results with manual reclassification. They asked whether Doppler skew could amplify the imbalance so strongly, and whether faint signals could account for so consistent a result across hundreds of galaxies. Again and again, the central finding survived. While uncertainties remain, each reanalysis leaves less comfort that bias alone explains the trend. Still, science thrives on further checks, and the appropriate next steps are clear. Independent groups must revisit the very same images with fresh methods and different classification strategies. Algorithms can be tested against human reviews, and mirror image experiments can serve as guards against lopsided annotation errors. Most importantly, analysis of other JWST deep fields beyond Goods S can show whether the tilt holds across new regions of cosmic history. Only through these comparisons can the community move from hints and patterns toward confirmation or rejection. Evidence from other observations already complicates the picture. Earlier telescopes, like Hubble and ground-based surveys, had seen small but noticeable imbalances in galaxy spin directions, though much weaker than the Webb numbers. The persistence of this effect across different instruments suggests it may not be a quirk of a single method. Moreover, work has shown that the asymmetry appears stronger at higher redshift, implying that the signature grows more obvious the farther back in time we look. If the imbalance is tied to faintness or measurement limits, one might expect the opposite. Such consistency across instruments and epochs is unsettling to those who would prefer a tidy explanation rooted in bias. Even the possibility that the Milky Way's own rotation might distort observations has been raised. If the motion of our galaxy influences how distant light reaches us, perhaps it skews detection in a way not previously appreciated. But the speed of our own rotation is generally considered too slow to leave a strong imprint, making this solution unlikely unless something fundamental has been overlooked. Either way, this proposal highlights the lengths to which scientists are willing to stretch current ideas before turning to radical new models. At this point, the community stands divided. One perspective holds tightly to caution. Until the imbalance is validated by further fields and methods, the possibility of error cannot be excluded. On the other side, the persistence and crosschecks already performed lend weight to the idea that something real may be encoded in those spins. Rather than declaring one path correct, researchers stress that both possibilities warrant testing. Bias may explain the imbalance neatly, but a cosmic origin cannot yet be dismissed. especially if independent analysis across multiple fields repeats the same orientation preference. The debate remains unresolved, but its endurance changes the conversation. Each repeated confirmation weakens the claim that illusion alone is to blame. Slowly, unease builds that we may be glimpsing not merely error, but a genuine imprint of deeper forces acting on the universe. From here, the natural question emerges. What if the imbalance is authentic and the machinery shaping entire galaxies reaches far beyond normal formation scenarios? That possibility opens a path toward ideas far more radical than instrumentation bias, and it is precisely where the discussion must go next. The radical alternative. Now for the bold hypothesis, speculative but taken seriously by some researchers. It suggests that the strange preference in galaxy spins may be more than a product of bias or chance. Instead, it could be the faint imprint of a much larger structure, a universe born inside a black hole. This idea is not entirely new. In 1972, physicist Gaurav Pathria first proposed that a black hole could contain an entire universe within its interior. More recently, Nikodem Poplawski developed a version based on spin and torsion in Einstein-Cartan gravity, suggesting that the collapse of matter in a black hole does not end in a singularity but rebounds in a bounce, spawning a new expanding cosmos inside. In this view, what we call the Big Bang was not absolute creation from nothing. It was the rebound from gravitational collapse in a parent universe. The description draws directly from relativity. A black hole forms when matter collapses so tightly that spacetime curves around it, trapping everything, light included, beyond its event horizon. For an outside observer, the horizon marks a point of no return. Nothing escapes back across it. Traditionally, the interior is treated as a singularity, a state where our equations break down. But in alternative cosmologies such as those worked on by Poplawski, the interior instead becomes an expanding region of spacetime with its own arrow of time. For inhabitants inside, that expansion is experienced as a universe much like our own. Crucial to today's debate is the role of rotation. Real black holes rarely sit unmoving. They often spin, carrying angular momentum from the matter that formed them. This rotation drags spacetime in what's called frame dragging. If our universe arose inside such a rotating black hole, then part of that angular momentum could cross into the newborn universe at the moment of bounce. As galaxies later formed, that inherited rotation might show itself as a preferred orientation still visible billions of years later. The imbalance seen by the James Webb Space Telescope, therefore, becomes tempting as an indirect clue. From a theoretical standpoint, the attraction of this model is that it doesn't abandon Einstein's equations. Black holes already exist. Their solutions, the Schwarzschild solution for static ones and the Kerr solution for spinning ones, are exact parts of general relativity. These solutions allow interior regions independent of the outside universe. If those inner regions expand instead of collapsing, nothing more exotic needs to be invented to describe them. In Poplawski's extension with torsion, quantum effects prevent matter from compressing into a true singularity, making the bounce physically consistent. What was once just a mathematical thought experiment thus gains observational relevance. The Webb imbalance places this line of theory in a new light. If galaxies are not evenly distributed in their orientation, then perhaps we are seeing fossil evidence of rotation passed down from a parent black hole. Cosmological ancestry in this picture is not metaphorical but literal. Like a fingerprint surviving across generations, the global axis of a former universe leaves its mark on ours. It is important, however, to stress the obvious caveat. This hypothesis is extremely hard to test directly. By definition, the event horizon cuts us off from the outside parent universe, so no signal or photon can cross back to verify the story. Proponents therefore rely on indirect evidence such as statistical imbalances, alignments, or patterns that isotropic Big Bang cosmology cannot easily explain. JWST spin asymmetry is provocative precisely because it fits this category. It is subtle, unexpected, and potentially consistent with inherited rotation. At the same time, one reason the idea holds interest is that it does seem to offer natural answers to long-standing puzzles. Standard cosmology uses cosmic inflation, a short phase of faster-than-light expansion, to explain why the universe appears so smooth and uniform on large scales. But if the entire cosmos emerged within a black hole, that interior would already be globally connected at its birth. Uniformity follows automatically from the geometry, not from a hypothetical field. Likewise, the preferred axis becomes comprehensible. It was set by the spin of the parent object long before galaxies existed. Skeptics counter that the hypothesis can too easily shift into untestable territory. If every black hole creates its own universe hidden behind a horizon, then those interiors are inaccessible and remain beyond any direct experiment. Without falsifiable predictions, critics argue, the concept risks slipping outside science and into metaphysics. This is why most cosmologists treat it cautiously, not as a replacement for the Big Bang model, but as one of several speculative frameworks waiting for stronger evidence. Yet history shows why some theories worth exploring begin in speculation. Expansion itself was once dismissed until Hubble found galaxies receding. Black holes were labeled curiosities until decades of data forced them into mainstream science. Even Einstein hesitated at the implications of his own equations. In all of these cases, bold proposals became indispensable parts of physics once observations caught up. That is the status the black hole interior model occupies today. Improbable to some, intriguing to others, but no longer dismissed outright. Advocates also point to the hierarchical picture it paints. Every black hole in our universe could potentially give rise to its own child universe, invisible to us but real within its own horizon. In this nested system, universes branch like a cosmic tree, each carrying forward properties from its progenitor. In such a setting, the arrow of time itself may be inherited, passed through the horizon as matter collapses in one universe and rebounds as expansion in another. This narrative offers a striking reinterpretation of the Big Bang. Instead of an unexplained singular event marking the beginning of everything, the Bang becomes one of countless transitions, matter crossing a threshold, the interior inflating, and a new universe taking shape. Our own existence, then, represents not the birth of reality, but one episode in an ongoing cycle of gravitational collapse and rebirth. Galactic spin imbalance becomes an observational hint that continuity may stretch across universes, rather than ending at a singular origin. Despite the appeal, no one can escape the problem of proof. Unless further patterns emerge, coherent alignments in other fields, relic imprints visible in the cosmic microwave background, or links to black hole physics that tighten predictions, the hypothesis remains tentative. But what Webb uncovered has breathed new life into the conversation. It gives theorists a concrete feature that standard cosmology struggles to explain, and this, more than anything, is why the model cannot be dismissed outright. If correct, the idea reshapes how we think of place and boundary. The vast cosmos above our heads would not be infinite in the usual sense but bounded, its observable edge representing not nothingness beyond, but the hidden surface of a parent black hole. What we interpret as the Big Bang horizon might instead be the shadow of that parent's event horizon, containing us completely within it. From that perspective, our universe is not free-floating at all. It is enclosed by a structure larger than itself, locked behind a gravitational wall we cannot cross. And here lies the crucial step. If our cosmos truly sits inside such a boundary, then the limits of observation and the definition of the universe itself take on an entirely different meaning. Schwarzschild cosmology and cosmic prison walls. Schwarzschild cosmology presents one of the most radical reframings of modern physics. It rests on the simple but striking possibility that the interior of a black hole could function as an entire cosmological region. In this framing, the event horizon, the surface where escape velocity equals the speed of light, becomes identical with the observable universe's boundary. From our viewpoint inside, what we call the universe is just the enclosed spacetime region hidden from the outside by that horizon. In ordinary cosmology, the limit of what we can see is set by time. Light from the farthest galaxies has a finite age, stretching only as far as the universe has existed. In Schwarzschild cosmology, that limit is not simply temporal but structural. The ultimate horizon is not how far light has traveled since the Big Bang, but the unpassable surface of a black hole's gravitational boundary. Beyond it, no photon or signal can ever slip through to be seen. The difference seems subtle, but it fully rearranges how we think about cosmic structure. This shift raises immediate consequences for how astronomers describe the universe's limits. Conventionally, we imagine the cosmos as a bubble of expanding space arising from an initial singular creation event, with a visible edge set by the distance light has managed to cover. By contrast, within the Schwarzschild frame, that visible edge is nothing other than the black hole's horizon itself. What looks to us like an expanding universe bounded by age is actually the interior of an object whose outer surface seals us in. Physicists such as Raj Kumar Pathria and I.J. Good helped outline this notion decades ago, hinting that the event horizon of a black hole could double as the same horizon we describe in cosmology. More recently, Nikodem Poplawski has expanded the idea with a theoretical mechanism rooted in Einstein-Cartan gravity, where torsion, the intrinsic spin of matter interacting with spacetime, prevents the collapse to an absolute singularity. In this model, matter falling inward rebounds in a bounce, giving rise to expansion within the newly created region. Though highly speculative, this proposal solves the singularity problem that plagues the standard view of black hole interiors. A useful way to think about the horizon is through analogy, though with caution. Imagine being in a room where the walls cannot be touched and cannot be crossed, no matter how far you walk. To a person inside, the space feels limitless, but in fact it is bounded. Similarly, within Schwarzschild cosmology, stars, galaxies, and radiation all exist in an enclosed volume. Expansion happens inside the cage, but the limit is structural. This metaphor, however, must not be mistaken for observational proof. It is an interpretive tool to illustrate a very abstract consequence of general relativity. An important implication concerns the Big Bang itself. In mainstream cosmology, the Big Bang is treated as both a spatial and temporal origin, the moment when not only matter and radiation but time itself began. Under Schwarzschild cosmology, however, the Bang becomes the unfolding of spacetime already embedded in a black hole interior. Our expansion is not from nothing, but from a prior collapse in some larger parent universe. What looks to us like a birth event is instead the rebound phase of matter crossing an event horizon and re-emerging as an expanding domain. This interpretation could, in principle, address some of the puzzles that inflationary theory was designed to solve. Observations show that parts of the cosmos separated by vast distances are surprisingly uniform, even though no conventional signal should have linked them since the Big Bang. Standard cosmology responds by proposing inflation, a short burst of super-expansion that smoothed everything out. Schwarzschild cosmology suggests an alternative. The uniformity is built in, because the black hole interior is already a connected region where causality was established at the moment of formation. From our position inside, the universe still appears immense. Billions of galaxies scatter across distances so large that light takes billions of years to reach us. Nothing about that impression changes under this model. What changes is the character of the outer boundary. Instead of being a horizon formed only by age and expansion, it is the event horizon itself, a hard limit where spacetime separates one region from another. In this sense, the cosmic microwave background functions as a visible limit, the last wall of radiation we can detect, But behind it lies not an endless continuation of space, but a barrier. Whether we imagine more reality outside becomes a philosophical question, because physical signals cannot bridge the gap. The challenge, of course, is verification. From within, one cannot conclusively determine whether the surrounding horizon is simply the natural boundary of expanding space or the gravitational seal of a black hole. Observations give no direct way to distinguish the two. This is why, despite its fascination, Schwarzschild cosmology remains a speculative framework. Bottom line, if we lived inside a black hole, the event horizon would look like our cosmological horizon, but proving that from inside is fundamentally difficult. Still, this framing strips away mysteries that conventional cosmology compensates for with additions like inflation. By rooting cosmic expansion in physics, we already know black holes, horizons, the bounce from torsion effects. It offers a self-contained explanation for large-scale features of the universe. The cost is a sobering one. The recognition that everything we measure might be confined within a gravitational partition we cannot ever see beyond. Philosophically, that realization is challenging. In science, we are used to the idea that better instruments extend our reach, opening deeper views into space and into time. Within Schwarzschild cosmology, no improvement in telescope or detector can carry us beyond the horizon. The walls of our universe, if they indeed are those of a black hole, are set by the structure of spacetime itself. This sense of enclosure naturally drives a further question. If the event horizon marks not the start but simply the surface of a much larger process, then what we call the Big Bang may not be a fundamental beginning. It could instead be one stage in a cycle, collapse outside producing a rebound inside, one universe giving rise to another. The very definition of beginning might be transformed if this perspective is correct. And that leads directly into the next question. Should we really think of our origin as a Big Bang at all, or instead as something closer to a big bounce? The Big Bang or the Big Bounce? For much of the last century, the Big Bang has provided the dominant description of the universe's beginning. It imagines all space and time compressed into a single state of infinite density, then suddenly expanding into everything we see today. But when scrutinized, that initial singularity raises more questions than it answers. Infinities in physics usually signal the breakdown of theory rather than an insight into reality. If the equations collapse into undefined quantities at the very moment they are meant to explain, then the beginning remains unexplained. This difficulty has motivated researchers to explore alternatives that preserve the predictive strength of physics at the limit of density. One of those alternatives has gathered momentum under the name of the Big Bounce. Rather than interpret the Big Bang as an absolute beginning, the bounce reimagines it as a phase change. A leading voice in this conversation has been physicist Nikodem Poplawski, who examined how matter behaves when collapsing into a black hole. His work suggests that the interior need not end in a singular dead end. Instead, the collapse may rebound into a new expanding region of spacetime. Likewise, physicist Enrique Gazdinaga has published models extending the bounce concept, showing how contraction followed by expansion could create a cosmos like ours. These perspectives place the bang within a wider sequence, collapse, rebound, expansion, rather than creation from nothing. The mechanism relies on known quantum and relativistic effects acting together. Under extreme compression, matter resists infinite collapse because of the quantum exclusion principle. Identical particles cannot occupy the same state, and this builds a pressure, sometimes called degeneracy pressure, that strengthens as density climbs. In a black hole collapse scenario, that pressure eventually grows strong enough to halt the crush toward infinity. At the turning point, the inward fall converts into an outward rebound. Within such a framework, an expanding universe emerges naturally, no singular point required. A simple analogy shows the process. Imagine a spring being forced inward. As it compresses, the restoring force increases until it reaches a peak limit, Further squeezing is impossible. At maximum pressure, the spring recoils and swings outward sharply. In a bounce cosmology, collapsing matter mirrors that spring. The tighter the collapse, the stronger the resistance until the system bounces. Internally, the rebound appears as rapid, expanding spacetime, indistinguishable from what cosmologists today call a Big Bang. But in this framing, the bang is a continuation, not a beginning. This picture also reshapes how we view black holes themselves. In conventional thinking, they are the cosmic graveyards of matter and light. But in bounce cosmology, every black hole may be fertile ground for new universes. The horizon acts as a one-way veil. To observers outside, matter is trapped. To those within, collapse seeds an expanding cosmos. Our own observable universe may therefore be the interior of a black hole formed in some larger parent universe. What looks like the singular start of everything could be only one stage in a hierarchy of nested cosmologies. The attraction of this approach lies in its conservatism. It does not propose unknown forces or speculative fields. Instead, it applies relativity to describe collapse and quantum mechanics to deny infinities. Where the Big Bang imports inflation to explain smoothness and horizon problems, the bounce argues these conditions arise naturally from the continuity of collapse and rebound. Such internal consistency makes it compelling as a serious working hypothesis rather than fringe speculation. Notably, bounce models bring testable consequences. Poplawski predicts that our universe should reveal a small positive curvature, ever so slightly closed in its geometry. If upcoming instruments measure such curvature with enough precision, this would provide evidence that supports the bounce over a perfectly flat Big Bang. Additionally, the theory proposes the survival of relic objects from before the bounce, compact remnants such as primordial black holes or neutron star-like objects. Detecting such relics in the early universe would serve as direct hints of pre-bounce physics, and could resolve puzzles like why enormous black holes appear so early, or what forms dark matter might take. The bounce perspective also changes how we understand the growth of structure. Standard cosmology suggests small fluctuations were blown up by inflation to seed galaxies and cosmic filaments. Bounce models argue the ripples were already present as quantum oscillations of spacetime during the contraction phase. The transition into expansion preserved them, giving rise to the cosmic scaffolding without invoking extra fields or forces. The irregularities that became galaxies in this view are fossils of a collapsing phase we can no longer see. Another strength is how bounce cosmology links gravity to quantum rules. The rebound only occurs because quantum principles intervene in otherwise classical collapse. That interplay between quantum exclusion and spacetime geometry forces a halt at finite density. It hints at a bridge between general relativity and quantum theory, an avenue long sought but rarely grounded in observable consequences. By pointing to how the laws might act together at extremes, the bounce emphasizes what is missing from the singular Big Bang picture. These models remove the formal singularity and shift the central question to what physics, likely quantum gravity, governs conditions at maximum density. Importantly, no researcher claims the bounce has been proven. What exists so far are coherent theoretical models, like those from Poplawski and Gastineaga, and plausible observable predictions. Precision measurements of curvature, relic searches, and improved early universe surveys will be needed for testing. For now, it remains one of the more grounded alternatives, resisting the baggage of imagined particles or forces while targeting the singularity problem directly. Even with indirect support, such as the discovery of massive black holes very early in cosmic history, caution dominates. A black hole with hundreds of millions of solar masses existing just 500 million years after the Big Bang challenges standard timelines. Bounce cosmology can explain it as a carryover object, but this link is tentative. Other astrophysical processes might also account for early giants. The evidence fits, but it does not clinch the case. Taken as a whole, Bounce cosmology does not resolve every mystery. Instead, it reframes the core puzzle. Instead of asking how a universe could come from nothing, we ask what larger context produces cycles of collapse and rebound. Does time stretch backward indefinitely across successive universes? Do each of these child universes inherit properties, such as curvature or rotation, from their parent? Or is there still an ultimate origin concealed further beyond? These questions remain open. What matters for now is that the bounce offers a logically coherent, physically rooted alternative to a singular beginning. It demonstrates how known laws can operate at limits where the classical Big Bang fails. If confirmed, it rewrites origins not as a one-time creation, but as part of a continuous sequence embedded in deeper layers of spacetime. This leaves us with a provocative possibility. The patterns we observe today may retain imprints from a preceding universe. Subtle signatures encoded during the bounce could still be visible across cosmic structure. Among the most intriguing of these are patterns of motion, the way galaxies rotate, the directions they align, and whether, taken together, they trace the memory of a prior collapse. Rotation written across the cosmos. When Webb's deep field imaging was analyzed, one fact immediately stood out. Among 263 young galaxies in the JWST field, about 60% appeared to rotate clockwise, while roughly 40% went the other way. This imbalance becomes more striking at higher redshifts, where the skew appears stronger the further back in time astronomers look. Earlier ground-based surveys, including SDSS, PAN-STARRS, and the Dark Energy Survey, had already hinted at smaller asymmetries with some dependence on distance, though none with the clarity and depth achieved by Webb. Taken together, these results point toward a repeating pattern that may stretch across the observable universe. This is not without contention. Some independent analyses of similar datasets have found comparable asymmetries, while others report near-null results, depending on the classification methods used. Researchers debate whether statistical methodology, image processing algorithms, and photometric biases could be shaping the signal. The balance between real astrophysical signal and subtle observational artifacts remains in question, which makes reproducibility across instruments essential for evaluating the claim. Still, what keeps this signal in the spotlight is its persistence under different circumstances. Webb's data confirms that even galaxies just a few 100 million years after the earliest stages show a pronounced preference. The older the light, the stronger the imbalance seems to be. Such a trend pushes against explanations rooted in local effects or observational quirks alone, because it suggests the directional preference was present from the beginning, rather than introduced gradually over time. Visualizing these results can feel abstract. To simplify, imagine looking across billions of light years and finding that the majority of remote galaxies appear tilted the same way, like compass needles leaning slightly together. If random assembly governed galactic birth, orientation should scatter evenly with no global bias. Instead, the proportions we measure hint at a deeper order. For scientists used to treating isotropy, the premise that the universe looks the same in all directions at large scales, as a foundation, this imbalance puts one of cosmology's key assumptions under pressure. The challenge is to place these observations in context with other cosmic data. For decades, astronomers have debated peculiar alignments in the cosmic microwave background, sometimes called the axis of evil, where temperature fluctuations show a mild but unusual large-scale orientation. Though still disputed, some wonder if these alignments could connect in principle with the galactic spin results. Likewise, anisotropies in gravitational wave backgrounds or in the orientation of cosmic filaments could be read through the same lens. The possibility emerges that we are glimpsing a consistent underlying direction, not confined to galaxies alone, but pervading the structures of the entire cosmos. At the same time, Scientists remain wary of allowing one striking dataset to reshape decades of theory without corroboration. Even within Webb's results, cataloging galaxy spins requires careful choices and unavoidable uncertainties. Faint galaxies often blur into elongated smudges rather than clean spirals, making classification ambiguous. Both algorithmic and human annotations can quietly lean toward a preferred spin direction, especially when images are noisy or incomplete. To counteract that, researchers mirror galaxies, invert images, and run blind tests against algorithms. And even then, small biases can creep in. Reaching statistical significance doesn't remove the need for deeper testing across other fields of sky. Ground-based observations add weight but also complexity. The Sloan Digital Sky Survey covered vast regions of the sky at lower resolution, flagging a subtle spin imbalance that matched what Webb later saw more sharply. Pan-STARRS and the Dark Energy Survey added independent glimpses of the same asymmetry, though with lower confidence. What emerges is not a single clear experiment but a mosaic of overlapping hints, each pointing in the direction of anisotropy while leaving room for doubt. To many astrophysicists, this is exactly how cracks in established models begin, through independent results that refuse to fade. The scale of the phenomenon, if real, is difficult to grasp. Galaxies observed in the JWST field are separated by billions of light years. No communication or gravitational pull could align their spins in such synchronized fashion. They are too far apart and too young to have coordinated through known physics. That distance strengthens the case for a cause present before their formation, encoded across cosmic space itself. If these galaxies rotate preferentially in one direction, because of conditions set before their birth, then cosmic history may bear markers of something that existed prior to the expansion we call the Big Bang. This line of reasoning captures why some researchers view galactic rotation as the cleanest kind of cosmic signature. While abundances of chemical elements or distributions of stars can evolve through stellar generations, angular momentum is harder to erase. Once imparted, rotation tends to persist, carried from large scales to small. In that view, spin is not accidental. It is a fossil property, one that galaxies still display billions of years later. The imbalance is not just about numbers. It is about whether the universe remembers an initial condition through its rotation. Nevertheless, the cautious path is to hold competing explanations constantly in view. Perhaps unseen systematic effects are shaping classifications. Perhaps faint galaxies at the edge of detectability skew statistics simply because the dimmest features are hardest to interpret. Perhaps cosmic rays or noise in detectors mimic subtle spiral structures. These possibilities cannot be ruled out, and it is exactly the job of further surveys, with Webb, Hubble archives, and future telescopes, to test them against the alternative claim that the pattern belongs to the cosmos itself. What strengthens interest now is that the effect does not appear as a one-off anomaly. It shows up across multiple instruments, wavelengths, and methodologies. Even when weaker than Webb's numbers, ground-based surveys measured the same tilt. And crucially, the magnitude of asymmetry seems tied to redshift. The further back in time we look, the more the skew shows itself. That scaling relation is not easily explained away and may be the strongest argument in favor of a real astrophysical signal. The practical next step is large-scale consistency. Astronomers will need to confirm the imbalance in multiple independent fields of the sky, ruling out a role for our own position, the direction of the Milky Way, or the peculiarities of the galactic poles. If the same preference recurs across unrelated patches, statistical confidence grows sharply, shifting the narrative from anomaly to established fact. Only then does theorizing about deeper causes move onto firmer ground. If it survives those tests, the idea that galaxies across the universe share a common tilt would rewrite the principle of isotropy. It would mean not only that rotation carries memory, but that memory extends all the way to the structure of the universe itself. In such a case, order triumphs over randomness, and every galaxy wheel we catalog becomes another reminder of underlying coherence. This is where the significance of black holes re-enters the picture. If rotation remains the most enduring cosmic signal, then one natural place to look for its origin is in structures already known for spinning at extreme scales: black holes. The possibility arises that these objects are not just gravitational sinks, but also markers of connection, each horizon hiding more than destruction. From the notion of a global spin preference, one step further leads to a profound question. Do black holes themselves shape the persistence of universes beyond their own horizons? Black holes as cosmic gateways. The subject of black holes as more than destructive objects has grown steadily in recent decades. Traditionally seen as final graves for matter and energy, they have instead been reimagined by some researchers as possible gateways. In this view, a black hole is not only a place where information disappears, but a frontier that may conceal entire regions of spacetime, hidden from external observers. The proposal is not rooted in speculative fiction, but in attempts to reconcile general relativity with the limits of quantum mechanics under extreme density. From an external perspective, the event horizon marks disappearance. Signals that cross it are lost to anyone on the outside. Yet relativity allows the mathematics of spacetime to continue beyond that surface. To an observer who could exist on the inside, the story does not end, it begins. In principle, the interior could unfold as a self-contained expanding region of space and time, developing structure just as our universe has. This scenario has led theorists to consider whether collapses in apparent cosmos could seed domains that, from the inside, resemble complete universes. Important to note is that this line of thinking remains a hypothesis, one among several considered in the literature. Some researchers treat black holes as cosmic endpoints, others explore them as possible beginnings of new, disconnected realities. The claim that every black hole makes a universe is not established fact. Instead, it is an intriguing idea given limited observational support, sustained by theoretical reasoning that avoids singularities and proposes rebound mechanisms. Its strength lies in offering a continuity between collapse and creation, rather than a single rupture with established physics. To clarify the theoretical landscape, several models have been advanced to describe alternatives to a singular core. Proposals of regular or non-singular black holes attempt to smooth out infinities in spacetime curvature, allowing stable interiors that remain finite. Related ideas such as gravastars or boson stars replace the singular region with exotic quantum states of matter, turning what would be an infinite collapse into a high-density but stable configuration. Other research frames black holes as potential black stars, horizon-scale objects without a true singularity. Each of these approaches is designed to solve a particular problem, to keep density finite, and to prevent the equations of relativity from breaking down at the center. Another recent line of thought relates black holes not only to structure formation, but also to the acceleration of the universe itself. In the cosmologically coupled black hole (CCBH) hypothesis, developed through analyses including data correlated with the dark energy spectroscopic instrument, black holes might be linked with dark energy. In this scenario, as black holes grow, their coupling with cosmic expansion contributes to the pressure driving the universe apart. If true, black holes would not be isolated systems, but central players in the fate of the cosmos. None of these models are yet confirmed. Each is at the stage of hypothesis, but they demonstrate active effort to replace the image of black holes as unfathomable voids with a framework in which they participate in cosmic evolution. The motivation for such work is not only theoretical but observational. Discoveries with the James Webb Space Telescope have brought attention to early structures, galaxies and black holes more massive than expected at very young cosmic ages. Within only a few 100 million years after the assumed Big Bang, black holes hundreds of millions of times the mass of the Sun already existed. Standard growth models struggle to explain such speed. This puzzle has driven renewed interest in proposals that suggest some black holes may have carried properties across a bounce or inherited mass and structure from conditions prior to our visible epoch. At the heart of many of these models is the concept of a gravitational bounce. General relativity describes collapse, but quantum mechanics resists singularity. Under extreme conditions, densities may reach a finite limit, at which point contraction halts and rebound begins. The interior then expands in what to its inhabitants would seem like a big bang, matter streaming outward, space itself stretching, time flowing forward. Shaped this way, the origin of a universe is no longer creation from nothing, but transition from one state to another. In this picture, what appears to external observers as collapse inside a horizon appears inside as the start of expansion. Such duality has consequences for the arrow of time. Matter crossing an event horizon does so in one direction only. That one-way character establishes asymmetry. Inside any resulting region, time inherits a forward bias traced back to that crossing. Models including torsion, such as those explored by Nikodym Poplawski, argue that spin coupling in Einstein-Cartan gravity makes this arrow an inevitable property. In effect, the passage through horizons writes directionality into causality itself. The persistence of a forward arrow from collapse to rebound is what allows inhabitants inside a new region to experience time as consistent, even though for external observers everything ended at the boundary. Extending this reasoning, theorists have asked whether black holes could form a branching structure of realities. Each collapse would, under some interpretations, generate a new domain of expansion. From an external vantage point, such branches remain sealed, inaccessible across horizons. From inside each branch, the cosmos looks complete and self-contained. This branching framework is highly speculative and resistant to direct verification, but it has gained attention as a logical consequence of combining relativity and quantum exclusion principles. It implies a multiverse of nested universes, though this remains a conceptual possibility rather than an empirically supported claim. From a scientific perspective, what matters most is not the imagery of these proposals, but their implications for real puzzles. The early appearance of massive black holes and unexpectedly mature galaxies fits uncomfortably within standard timelines. An interpretation that links collapse, rebound, and inherited properties offers an alternative way to understand that tension. Though the evidence is indirect, it aligns with predictions that bounce-like processes might deliver pre-assembled structures into new stages of cosmic history. Even so, astronomers know this remains one interpretation among many. Competing explanations invoke novel growth mechanisms or unknown energetic processes, and testing will require years of accumulating data. The potential scope of such ideas reaches deep into physics itself. If black hole interiors genuinely connect to expansion regions, then gravitational dynamics could provide a natural origin for dark energy, cosmic inflation, and time's direction, all within the geometry of spacetime. Likewise, if objects such as gravastars or boson stars exist, they would represent new matter states that bridge astrophysics and quantum field theory. These concepts remain outside direct observation, but they are motivating factors in theory and in planned observational programs. Instruments probing gravitational waves, horizon-scale shadows, and cosmic expansion signatures may provide constraints that confirm or falsify the models. Ultimately, the reconceived role of black holes, from destroyers to possible gateways, reshapes the narrative of astrophysics. They remain dangerous objects that devour matter, but they may also be generative, giving rise to new regions of space hidden from our direct view. The language of portals or gateways captures the conceptual shift, but whether they truly play that role remains an open question. For now, the evidence rests on theoretical consistency, and indirect tensions with observation, not on direct proof. This leaves science in a delicate position. Black holes may be hiding far more than destruction, perhaps even origins. But while the mathematics permits such interpretations and observations create pressure for new models, the limits of access remain absolute. The very boundary that makes them candidates for cosmic gateways is also what prevents us from seeing directly what occurs within. It is this paradox that shapes the next challenge. The limits of knowledge. The discussion of black holes as possible gateways raises a much sharper question. What can we actually know? Physicists refer to this boundary as the ** limits of knowledge *, and nowhere are those limits more clearly drawn than at a black hole's event horizon. This invisible surface is where escape velocity matches the speed of light. Nothing crosses back out. No particle, no signal, no photon can return once it has gone beyond. From the standpoint of external observers, the horizon establishes a permanent blockade that forbids direct insight into whatever occurs inside. While this barrier cannot be broken, astronomers do have powerful external tools for studying conditions just outside it. Observations of accretion disks reveal how gas flares to extreme temperatures before plunging across the horizon. The Event Horizon Telescope captured the dark silhouettes of supermassive black holes in 2019 and 2022, providing the first visual confirmation of the predicted shadows. Mergers of stellar mass black holes, caught through gravitational waves, now reveal how spacetime itself is stirred and shaken around them. These probes allow us to test the external profile of black holes, their mass, their spin, their horizons, yet none of them tells us what lies within. The progress in gravitational wave astronomy has been particularly striking. Detectors such as LIGO and Virgo have registered mergers of black holes with precision high enough to test predictions of general relativity. The data shows black holes behave as Kerr objects, spinning solutions of Einstein's equations. Even subtle laws such as Hawking's area theorem, which states that the combined surface area of event horizons cannot shrink in a merger, have held up under scrutiny. This is evidence that the mathematics describing black holes as external observers see them is robust. But those verifications all occur outside the horizon. They confirm the rules of spacetime around the object without granting access to its interior. The blockade leaves us with theory to describe the unseen side. General relativity insists matter falling through continues toward a singularity of infinite density. Yet many physicists argue the singularity is not physical at all, but a sign that the equations have reached their breaking point. To patch that failure, researchers explore possibilities such as loop quantum gravity, torsion-based models that create a bounce, or structures like regular black holes and gravastars designed to avoid infinities altogether. None of these alternatives can bypass the communication barrier, though. At best, they keep equations consistent while acknowledging that what happens past the horizon cannot be directly tested by observation. This impasse is sharpened by the information paradox. General relativity appears to say information vanishes inside black holes, erasing physical history as matter collapses. Quantum mechanics, on the other hand, demands information is never destroyed. The contradiction is unresolvable within current frameworks. It stands as a direct collision between the two most successful theories of physics. The paradox deepens the recognition that horizons are not just astrophysical structures, but boundaries in our understanding of natural law. If universes are created within them, then the very place of our origin exists where theory itself fractures. For this reason, alternative pictures cannot be brushed aside as mere imagination. Regular black hole models that remain finite at their core, gravastars supported by exotic matter states, or even black hole mimickers that emulate horizons without containing them, all are attempts to preserve consistency where singular collapse undermines it. Each keeps the same rule intact: what crosses in never comes out. The horizon enforces secrecy regardless of what theoretical structure lies beneath it. We can describe possibilities, but the evidence remains out of reach. Scientists therefore turn to anomalies in the wider universe as indirect markers. If galaxies appear to spin disproportionately in one orientation, perhaps that is a trace of inherited angular momentum. If enormous black holes exist unreasonably early in cosmic history, perhaps their seeds carried across from a stage predating our own expansion. These signals do not open a window into the interior of black holes, but they hint at processes inconsistent with randomness, encouraging speculation that the fingerprints of hidden dynamics survive in the universe at large. This method of reliance on indirect evidence is not unusual in science. No one has stood at Earth's core, yet the waves of earthquakes tell us its structure. No one has ever seen a quark, yet scattering experiments confirm their existence. The crucial difference with black holes is that no experimental improvement can cross an event horizon. The interior gives off no waves, no radiation, no particles that could betray its secret. If new universes unfold inside, they leave at most quiet echoes, statistical asymmetries in cosmic data, small shifts in structure, puzzling alignments that can only be interpreted from a distance. The event horizon therefore becomes more than an astrophysical boundary. It functions as a philosophical marker of where observational science ends and inference begins. Scientists can test external metrics against general relativity with extraordinary precision, and they can refine models to describe consistent possibilities within. But the direct content of the interior is unavailable. Verification, in the usual sense of experiment and confirmation, breaks down at the very point it is needed most. The paradox is clear. We can extract immense knowledge about the outer behavior of black holes through tools such as EHT imaging, accretion signatures, and gravitational waves. These observations continue to confirm predictions of relativity and deepen our understanding of how horizons shape their surroundings. Yet we cannot obtain direct facts about interiors, singularities, or bounces. No pathway carries information out once it has crossed the boundary. We can test the outside. The inside remains inaccessible, so cosmological inferences must be indirect. And it is those indirect inferences that point to unsettling possibilities about cosmic history. If the fingerprints of horizons are written into galactic rotations and the timing of structure, then the universe around us carries memory of past events that we cannot see directly. That recognition leads to a broader reconsideration of scale and place, raising the possibility that what we call a universe may be only one part of a much wider system. Rethinking our place in the infinite hierarchy. Rethinking our place in the infinite hierarchy begins with a clear shift in perspective. If black holes carry the potential to generate new universes, then what we call the universe may be only one chapter of a much broader framework. Each collapse of matter into a black hole could ignite an interior spacetime expansion, invisible to the world outside. From within, that expansion looks like an entire cosmos. Taken together, the pattern resembles a layered system of realities, an endless branching where each horizon hides a new domain. Instead of holding one unique universe, existence may contain countless nested ones. Our own universe becomes just one of many, defined less by singularity than by position along a branching sequence. For a long time, humanity's sense of place has been repeatedly humbled. First, Earth was dethroned as the cosmic center, shown instead to orbit the Sun. Later, the Sun itself became one star among hundreds of billions in the Milky Way. Eventually, the Milky Way proved only one galaxy in a larger sea. Now, rotation patterns seen in Webb's earliest galaxies may be pressing us toward the deepest loss of centrality yet, that our whole universe may simply be one stage in a repeating hierarchy. In that setting, our cosmos is not privileged any more than Earth once was. It is one node in a chain that stretches far above and far below our horizon, and possibly has no beginning or end. This generational chain does not stop at a single step. If universes form within black holes, then the process repeats endlessly. A parent universe creates offspring. Those offspring harbor black holes, and from those collapse new descendants emerge. Each cycle adds another link to the chain. The branching grows in all directions until the system resembles an infinite genealogical tree of spacetime. Looking from within, each universe feels isolated, bounded by its own horizon. But the larger structure is not isolation but multiplicity, a nested family of universes. This changes the very aim of cosmology. Instead of assuming we study existence itself, our science may be confined to just one branch on an incomprehensibly vast structure. The consequences for physical law are striking. For decades, physicists have puzzled over why constants in our universe, the masses of particles, the strength of gravity, the density of dark energy, have the precise values they do. The existence of stars, galaxies, and life depends critically on them. Even a slight variation could destabilize the cosmos or render it barren. Within standard cosmology, this fine-tuning feels inexplicable. But in a framework of nested universes, the puzzle changes. Each universe might be born with its own set of constants. Some would collapse quickly, some would expand too fast for galaxies to form, others might remain lifeless but stable. If many exist, then it is not surprising that we happen to live in one where conditions permit complexity. Observers can only emerge in universes that support them. Still, clarification is critical. If many universes exist with varying physical constants, anthropic selection explains why we observe life-friendly values. This is a plausible logical consequence, but not direct evidence of a multiverse. A nested universe picture would make fine-tuning less puzzling, because selection effects operate across many branches, but this remains speculative and untestable so far. The scenario offers reasoning, not confirmation, and the step from possibility to fact is one science cannot take yet. Thinking in terms of variation across universes opens another angle on how our physical principles may fit into a wider range of possibilities. Imagine a universe where gravity is stronger. Stars would burn quickly and collapse before planets form. In another, if dark energy is far greater, cosmic expansion would scatter matter apart at such speed that galaxies might barely assemble before dissolving. Each set of rules defines its own outcome. Our universe shows one pattern, but nothing guarantees that pattern is universal. In the larger structure, every rule set may occur somewhere, producing diverse outcomes inaccessible to one another. What unsettles many is how this hierarchy fractures the sense of one definitive reality. For centuries, we assumed the stars above us, the galaxies stretching out, and the fabric of spacetime itself represented everything. Under the nested model, that belief collapses. What we call reality disperses into countless sibling domains, each divided by unreachable horizons. Our universe no longer contains all of existence, but only one installment within an ongoing cycle. Somewhere beyond our horizon, other universes may exist, older, larger, stranger, but we will never cross into them. And inside the black holes of our own universe, entirely new universes may already be expanding, severed forever from us, unaware that we once existed. The hierarchy underscores our limits. However powerful our telescopes become, they cannot show us outside our horizon. However intricate our experiments, they cannot follow matter into our black holes. We rely instead on indirect signs, a skew in galaxy rotation, alignments in the cosmic background, unexplained early black holes. These may be hints of inheritance, faint evidence that our universe carries echoes of another, but full confirmation lies beyond reach. Science confronts here not just practical limits of tools, but conceptual limits of its subject, an ultimate inaccessibility written into spacetime itself. Yet imagining this possibility changes how we think of origin. If universes nest within black holes, then each link carries ancestry. Ours springs from a parent, which itself comes from another, and the chain continues without clear origin. Existence then resembles not a singular miracle but a generational cycle. Expansion in one universe is seeded by collapse in another, and the story repeats. In this framing, galaxies and stars, including ourselves, are not isolated creations but stages in a chain of succession, embedded in a history far longer than we can ever measure. There is perspective to gain from this. If the hierarchy is real, then we do not live in the universe. We live in a universe. Ours happens to allow stability, chemistry, and biology, but many others may not. The broader reality contains a diversity incalculably wider than anything we can witness. That possibility does not diminish the significance of our lives or our universe, but it reminds us that what we encounter is only one version of existence among many. The horizon of our cosmos is as much a boundary of knowledge as a boundary of space. We cannot look beyond it, but we can reflect on the implications of what it might conceal. Here a practical question naturally arises. If our universe is not unique, what would that mean for why we are here? The idea that life emerges only where conditions permit it is unsettling but also empowering. It suggests our place is not random but contingent, an outcome set by the deeper branching system of universes. For you as a viewer, here's the question to consider. If we're one of many universes, what does that say about meaning and origin? Leave a comment with your view. This conversation gains depth when more perspectives are included. In the end, the hierarchy offers humility. It sets our universe back into a continuum of structures larger and more layered than we imagined. We may not prove it, and we may never step outside our horizon to test it directly. But thought itself adapts, and even speculation matters when evidence hints at directions beyond the standard model. Whether the cosmic skew is error or evidence, whether the hierarchy exists or not, the result is the same. We must expand our picture of reality and accept that our current theories may not capture its entirety. From there, the largest question remains unresolved, and it waits in every piece of data we examine. The unfinished story of cosmic origins. The unfinished story of cosmic origins lies at the point where observation pushes past what our current theories can explain. The debate now rests between competing models that draw very different pictures of how everything began. On one side stands the Big Bang, long the dominant explanation, proposing that space and time themselves emerged from a singular event, followed by cosmic inflation to smooth irregularities. On the other stands the Big Bounce and black hole interior models, which argue that collapse and rebound created what we observe today. Both approaches aim to explain the same evidence, but they diverge in their assumptions about beginnings, ancestry, and the very nature of space and time. The imbalance in galactic spin revealed by Webb has sharpened this contrast. The numbers drift too far from randomness to sit comfortably within standard expectations, leaving researchers with the task of either uncovering hidden bias in the data or rethinking the foundational story of origins. The challenge is not a simple contest between doubt and belief. It reflects how science operates under the limits of evidence. Measurements carry errors. Classification of faint, ancient galaxies is prone to distortion. A conservative voice may argue that what Webb saw is just the byproduct of faint features barely visible, aggregated across hundreds of galaxies. Yet the persistence of asymmetry, not just in Webb data but hinted at in earlier ground-based surveys, makes that explanation harder to sustain. At the same time, the alternatives demand a profound revision of cosmology. If the universe originated inside a black hole or through a cyclical rebound, then the neat singular start of the Big Bang must be replaced by an engine of continuity, linked to conditions beyond what we can directly reach. Still, Webb's result cannot be read as proof of one model over another. Observations are compelling, but they are not absolute. A modest measurement bias, when scaled across large samples, could still emulate an oriented cosmos. Science moves not with single results but with corroboration, repetition, and refinement. What makes Webb significant is not that it has solved the riddle, but that it has forced every existing explanation into stress. That is the measure of progress. Anomalies compel us to stretch theories until they either adapt or break. This is the situation now, cosmic spin preference still unexplained, yet impossible to ignore. At the heart of the problem lies the event horizon. If our universe is within a rotating black hole, then its parent environment is walled away behind that surface forever. If instead the origin was a rebound, we remain stuck inside one phase with no observational path to its predecessor. In both cases, boundaries exist beyond which no telescope or detector can reach. The limitation is not technological, it is built into spacetime itself. For this reason, many physicists regard the current situation as a marker that our frameworks remain incomplete. General relativity and quantum mechanics may both stand, but together they leave gaps too wide to ignore. The singularity problem captures that clash. Relativity insists on an infinite density at collapse. Quantum mechanics insists reality cannot reach infinite compression. Each domain functions well in its own territory, but at their intersection they contradict one another. The imbalance of spins glimpsed by Webb might not solve that conflict, but it points directly to where the resolution is needed. A theory of quantum gravity, whether through loop quantization, torsion, or string theory, must explain whether collapse ends in annihilation or instead rebounds into expansion. Until such a theory exists, arguments circle over incomplete descriptions, each bound to fail when pressed against the deepest questions. Moments like this matter because anomalies have historically driven breakthroughs. Mercury's orbit departed slightly from Newton's laws until relativity explained it. The peculiar shape of the cosmic microwave background revealed hints of physics beyond simple models, fueling inflationary theory. In the same way, the asymmetry in Webb's galaxies pushes at today's frameworks. Even if the imbalance ends up partly due to observational quirks, it has highlighted weak points in cosmology. The importance of anomalies lies not in certainty, but in pressure. They force theory forward. The two dominant models, the Big Bang and the Big Bounce, remain incomplete. The Big Bang suggests origin from nothing, yet cannot avoid singularity. The bounce avoids that singularity but replaces it with cycles that leave unanswered what defines the first. In both models, big questions remain unsolved. Why the constants have their values, why large-scale order exists, and why preferences such as spin skew appear so early. Webb's data hints that order was present even in primordial galaxies, challenging any explanation that begins with chaos alone. What this means is not yet clear, but the signal is undeniable. In this sense, the imbalance is less about the galaxies themselves and more about the limits in our methods of knowing. Astronomers can neither ignore the evidence nor fully resolve it with current tools. This makes the discovery instructive. It becomes an unfinished story, not a conclusion, but a page that forces the next chapter. Science progresses by confronting these tensions head-on, not by wishing them away. Whether the skew proves illusory or profound, it shows that the tools of cosmology must advance in step with the scale of the questions. What then is testable now? The practical next steps are clear. Independent teams must reclassify galactic spins across more deep fields. JWST's goods S must be checked against goods N, CERS, and future surveys. Advanced instruments such as DAISY and Euclid will offer large-scale measurements seeking anisotropies in structure formation. Precise determination of cosmic curvature, at levels sensitive enough to confirm or deny small positive values, will provide direct tests of bounce predictions. These are achievable with current and near-future technology. On the theoretical side, nothing less than progress toward quantum gravity can carry the explanation across the singularity divide. Models of non-singular black holes, torsion-driven collapse, or loop quantum scenarios must produce predictions sharp enough to test against data. Only then will cosmology move from speculation toward grounded understanding. This observation, therefore, forces two clear tasks for science. First, reproduce and verify the signal across independent datasets and teams, ensuring it is genuine rather than artifact. Second, develop theories of gravity and quantum mechanics that remove singularities and yield predictions capable of falsification. Both lines must work together. Without empirical checks, theory risks drifting untethered. Without theoretical advances, data risks piling up without deeper explanation. The unfinished story lies in that intersection, the effort to join what observation suggests with what theory can sustain. The James Webb Telescope has not given us resolution, but it has shifted the contours of the debate. Its data revives old questions about beginnings and forces sharper demands on theory. For cosmologists, this is not the closure of a story, but the opening of a new phase. Every unexpected signal now becomes a possible lead. Each quiet rotation of a galaxy is a reminder that the story of origins remains open. It is at this point that the discussion turns to possibility. The anomalies Webb uncovers may be pointing toward a broader revision in science, one that unsettles long-held assumptions yet offers the chance for new clarity. The quiet detail of galaxy spins might already hold within them the first signs of the next revolution in cosmology. Cosmology today stands balanced between certainty and speculation, and the discoveries from Webb highlight just how much remains unresolved. While our instruments provide remarkable clarity, they also expose questions that have no simple answers. In the JWST field, JWST found about 60% of 263 early galaxies rotating the same way, an outcome not expected in a random universe. The evidence leaves two major possibilities. Either subtle observational biases shape the data, or the asymmetry reflects something deeper, like a universe born within a black hole or through a cosmic bounce. Neither explanation is settled. Which explanation do you find more plausible, measurement bias, or a universe inside a black hole? Share your thoughts in the comments. We'll keep watching how new JWST fields and other surveys test this, and we'll report clear developments as they emerge.